Hello, everybody. Welcome to Approaching Zero, minimizing downtime during deployments. By the way, if you ever see Carlos Chacon around, tell him this color of green doesn't work that great when you're recording. So, my name is Kevin Fiesel. I am a Microsoft Data Platform MVP out of Durham, North Carolina. I am a manager of a predictive analytics team, and I have a blog called Curated SQL. The idea of Curated SQL is I'd like to try to find and link to 5 to 10 interesting posts per day on topics like database administration and development, R, Python, Hadoop, Scala, Spark, Power BI, reporting services, security, or anything else in that broad data platform space. So that's curatedsql.com. What I want to talk about today is how to minimize downtime for application deployment, specifically database deployments. So we have database code, tables, views, stored procedures, and the like. And I want to deploy changes while affecting end users as little as possible. So this is not a talk about HADR. I'm not going to get into the infrastructure portion of this. It's specifically application development. Ideally, we do this with zero impact to users. They keep on merrily using our system without even realizing that we're upgrading in the background. In practice, we won't get true zero, and I'll explain why in just a moment. Instead, we settle for approaching zero. I get close enough to it. So here's the flow for today. I'm first going to talk about what downtime means. Then we'll look at the process for deployment and a few different ways of making life simpler. After that, we're going to jump into a bunch of different demos about different ways of deploying different sets of code. Finally, I'll wrap things up with a case study, an actual thing that I did and that I found kind of interesting. So downtime. If you work at a company where, hey, I don't really have to worry about end users after 6 p.m., then you probably don't care too much about this. If your website has office hours, downtime's not going to be an issue for you. You just wait until your users are out of the office and you make whatever deployments then. If you have extended windows for that, great. But there are plenty of companies that don't really have those extended windows. So if users expect your systems to be up 24/7, you may not have a convenient time to take down your system for an hour or two and make your deployments. Now, users may be able to accept a degraded experience. It's a little bit slower during this deployment time for maybe a few minutes. But if they don't want actual proper system is shut off for upgrade, well, we're going to have to code around that. We need an approach that'll keep them happy while letting us push out code changes at a reasonable pace and also at a reasonable time. If you are a database administrator, I've been in this world before where I've had to make deployments at midnight, at 1 a.m. And sometimes that deployment fails. Then you have to figure out, okay, well, which developer wrote this code? Because this code's not going out. There's a syntax error. Can I fix it myself? Do I need to get that person on the horn? Is that person available? Are they already drunk and passed out someplace in the bathtub? It's hard to tell. And if you've ever dealt with developers, they often end up drunk and passed out in bathtubs. It's a thing that happens. So, all right. We're dealing with this as DBAs, and we're in really awkward hours already, and we're trying to get this code out. It's not a great situation to be in. So ideally, we would like to find a way to deploy, say, in the middle of the day when the developers are hopefully sober, at least at work. Now, here's my reasoning for why downtime is an intractable foe. Downtime, I'm defining it as any time users are unable to access the resources they need in your product. So if I try to open up your website, click, 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 and it's just spinning there, it's spinning, it's down. All right, from my perspective, I don't care if the reason is there are database timeouts because of long blocking chains. If it's because a server's gone down, your server room's on fire, your servers have exploded. If it's because a DNS entry has been inappropriately added, which is rerouting everything to somewhere else. For me, I don't care. If I click the button, the browser just spins and I don't get my web page back, your site's down. And from an end user's perspective, I may just have to fill in my last entries for the day, and that way I can go home. Well, if I'm sitting there waiting and waiting and waiting, and your website's just not responsive, I'm having to stay late at work, things kind of start sucking for me, and I take it out on your application. This app is just worthless. It's always down, it's always crashing, everything's terrible. So from an end user's perspective, we want to avoid that, of course. And here's why you can't get zero downtime. A table lock is downtime. So think about it this way. Take your biggest, meanest fact table in your environment and drop and rebuild a cluster column store index. Or do something that's an offline operation. Wait for the phone calls to come in, because they will probably come in if it's really that big, mean, nasty, and heavily used, where people are saying, hey, the website's broken. I can't get the report to finish. I can't, do my job. Many of these operations are going to take locks for short amounts of time. That amount of time is still greater than zero. It may be milliseconds. It may be microseconds. It's still greater than zero. But here's the thing. End users have a bit of grace. And that bit of grace is that we will accept sometimes a little degraded performance and are willing to accept, say, dubious answers for why. My favorite is, I don't know, must just be the network. Network is slow today. If you can successfully blame the network and have end users accept it, to me, that's a valid amount of downtime. And I say that a little bit tongue-in-cheek, but actually I'm kind of serious about it too. Because the network is slow means, oh, well, this page normally loads in 3 seconds. Right now it's taking 4 or 5. Oh, well, okay, I'm sure that in a little bit it'll be back to 3 seconds. And if that's true, end users don't really experience that real degradation. So for them, it's just part of doing business. It's the variance in accessing a website. There's going to be some natural variance. We don't always expect this page must load within X milliseconds, unless you have that as a requirement, in which case things get a lot more difficult. But generally we don't. Given this, why do we want to minimize downtime? Well, from the standpoint of users, it's pretty obvious. Fewer interruptions for them. They get to go home at a regular time. For developers, they get to make more changes. They get to move faster. They can be more agile. So they can give end users those fixes, those improvements. It helps their quality of life. For the database administrators, we get to deploy when people are in the office, when people are available, when they're not drunk, passed out in a bathtub, when they're merely just buzzed, hanging out, maybe like near the bathtub. So with that in mind, let's talk through the flow that I'd like you to think about in terms of deployment process. We're going to use a modified variant of blue-green deployments. So there is this concept of blue-green, and we're going to break it into 4 major phases. The first phase is a database pre-release. The idea here is, well, database pre-release is a state of mind. It begins whenever you're ready for it. So things that make sense to do in a pre-release process are changes that take a very long time, but don't affect users. Users should not notice that you're in a pre-release. So let me give you an example. Let's say we're going to take all the data from one very large table, move it to another very large table, and we're translating the data in between. So maybe we're changing column types, maybe we're consolidating multiple tables together. And while we're loading this new table, users are still hitting the old tables. They have no problem hitting the old tables. They don't even realize that there is a new table or that we're loading data into it. So this is the type of stuff that you do pre-release. Then, once all your pre-release is ready, you're prepped, you're ready to go to a release. This is where the fun begins. Database release can start on a fixed schedule, but it could run several times a day. We might see a degradation of services here, depending on the type of work that's being done. So here's where we push the majority of our changes. But we're supporting an application release with our database code. So again, blue-green model. I want to show you one variant of a blue-green deployment model where the number of application servers is fixed. There are other versions of blue-green where you can add and remove servers, and you can understand the same pattern here. It's basically the same concepts. So suppose we have 4 servers. Before the release, this is our application code. We have what I'm going to call old code running on all of the servers. So it's in blue. Now, we take 2 of the servers down. You can see app 3 and app 4 are now gray. They are taken out of the load balancer. Users are no longer going to hit those servers. They're just going to hit app 1 and app 2. During this time, you might have a degraded experience because you only have half of the servers. Hopefully, you have enough capacity, even with half of your servers, that you're still handling load gracefully. And by the way, if you don't have that capacity, you don't have to take half of them down. I could take 1 of the 4 instead of 2 of the 4. So please don't think this is mandatory. You must take down exactly half. It's not that inflexible. Nonetheless, we take app 3 and app 4, and we're going to load the new code onto those servers. During this phase, we have old code in blue, app 1 and app 2. We have new code in green, app 3, app 4. We need to be able to support both of them at the same time because we're bringing app 3 and app 4 back online. Our load balancer is perhaps recognizing that these servers are back up. We're running through our integration tests. We're running through some basic load tests, maybe bringing like 5% of traffic through these new servers just to make sure things don't collapse, they don't fall apart. Well, our database under the covers needs to be able to support that old code, app 1 and app 2, and new code, app 3 and app 4. So keep that in mind. After we're satisfied with 3 and 4, we're going to move all the traffic over to them and repeat the process with app 1 and app 2. Bring those servers down, put the new code on, bring them up, add them back to the load balancer once they've passed all integration tests, all deployment tests, and we're now in a new state. All servers are running new code. So rinse and repeat the next time you need to do a deployment. Finally, this is actually my favorite part. The database post-release is where we get to blow stuff up. We get to destroy things, remove columns, remove tables, drop procedures, get rid of old data. It's where we do the cleanup. I love that cleanup. I love deleting stuff. Database post-release can go on as long as you need it to. So it could go on for days after the release because end users won't know. They won't care. It won't affect them. So this is our state of mind. We have this 4-phase deployment process. And I'm going to help make life a little simpler for you. I'm going to make 3 key assumptions. Key assumption number 1, your code is in source control. Yeah, at this point, it's really got to be in source control. This is not even a, gee, you really should be doing this. This is, I don't want to work at your company if you don't have your database code in source control, because what happens when things get messed up? This is database code is code. Code should be in source control. That is a great way of protecting code. Number 2, you have an automated release process. Number 3, continuous integration pipeline. So, source control, my slide says it's not mandatory. I'm going to go full screen. It's mandatory. You got to have your code in source control. That database code, those stored procedures, those tables, those views, have that somewhere in source control. Git is the most popular source control system, but use whatever you want. You can use Mercurial, you can use SVN, CVS. I probably wouldn't use CVS at this point, but the specific system doesn't matter that much, just that you have it. Frankly, find out what the developers are using and use what they use. That's probably the easiest route. And I've known quite a few companies where developers were resistant about putting database code in source control, which seemed a little weird because they were also writing web code, application code. I would always ask them, well, why do you put that in source control? And then the answer is usually, for the obvious reasons why you'd have stuff in source control, well, I want to make sure that I don't lose that code if there's an error. I want to make sure that I have a successful backup in case a server gets destroyed and we need to redeploy things. I want to make sure that I have general protection. Then I say, why don't you do that for the data? I mean, the data is a lot more important than your application. Sometimes that works. Sometimes it works. Next, automated release process. Again, the specifics of what automated release tooling you use, don't really care. You can use Azure DevOps, Octopus, Jenkins, build it yourself, use some other third-party tool. Whatever works for you is good enough. In this case, what we're caring about is all scripts go and the release is consistent. I want to make sure that there are as few humans involved in the release process as possible, because humans make a lot of replication mistakes. If I have 40 scripts to run, the likelihood that I will run all 40 scripts in the correct order every time is vanishingly low. And, it's hard to remember, did I actually run script 27? It may not matter at the time, but then you get the script 34 and there's an error. And you have to try to figure out what happened. Or you run script 27 twice and, well, it deleted some data, but then the second time it deleted data it shouldn't have deleted. That's a sign of a bad script. So this is something that I want robots involved in rather than people. And with that, you get to this concept of continuous integration. My example of we deleted data and then we ran the script again and it deleted more data. That's a sign of a script that is not going to work in a continuous integration setup. For continuous integration, we want to make sure that our scripts are rerunnable. And we're constantly rerunning these scripts as needed in lower environments to test and make sure that everything still works as expected. So in addition to those 3 key things, those are the keys. If you don't have those, you're probably not getting close to zero downtime. Here are some simplification measures that will really help you out. The first one is to use Enterprise Edition of SQL Server. This will let you do things like rebuilding indexes online, partitioning tables, and that'll help make deployment easier. Read committed snapshot isolation will limit the amount of blocking that happens. It doesn't eliminate blocking, but it does reduce the risk of writing to tables, blocking reading from tables. Now, writers can still block writers. So where this makes sense is if I am, for example, adding a new column to a large table, I might be writing that data to the current table while my end users are reading the existing columns. If I don't have read committed snapshot on and I'm using read committed isolation, I run the risk that I am going to block my readers because I'm currently writing to that table. So by having read committed snapshot isolation on, I generally reduce that risk. Now, there are downsides to read committed snapshot isolation, and I would make sure that you understand what those downsides are and that you're doing this, that you can turn it on. Supposing that you can, I'd recommend it. It's usually a good default. The next bit, stored procedures. These act as an interface between your application and the code. So there's a long-going debate about stored procedures versus application code, just writing your queries in code. And I am definitely on team stored procedure. So here's coming at this from a data platform professional standpoint. If I'm talking to an application developer about stored procedures and they are kind of against stored procedures as an idea, my way of trying to help them understand the value of it is to say, look, stored procedures are an interface. I'm going to be able to guarantee to you that if you send in code, you send in these input parameters, I'm going to give you back data in this particular shape, and I'm going to make sure that things look right. No matter how the database changes behind the scenes, I'm going to make sure that everything is as you expect. So you can take that to the bank. If the database has changes, there are table changes, there are new columns are changed, data types are changed, that's all okay. I can protect you in that interface so you don't have to change your code. It's something that a lot of application developers don't think about up front, and it does feel like a little bit of extra work. But once you get to that point, it makes a lot of sense, and I think it helps app developers understand the value of those stored procedures. Last bit, database tests. I want to make sure that my code is still going to work after I've done a round of modifications. This will let you experiment a bit. It's going to give you the ability to experiment without adding risk. There are a couple of database platforms for testing. One of them is T-SQL-T. It is, I think, the most popular database test library out there. But you can write a series of in-unit tests. You could use Visual Studio's database tests. Quite frankly, you can have a script that you run in Management Studio that's a workbench, essentially. You've just created some select statements, some insert statements, and you run that thing. If the results look the same, you're good. You don't have to have a fancy test environment to get this to work. So we've laid out a lot so far. Laid out a lot of assumptions, laid out some process. Now let's get to some demo and understand changes, stored procedure changes first and foremost. So we're going to hit 6 separate scenarios in stored procedures. And instead of me talking through each one of them, I'd rather show you demos at this point. So let's switch over to Azure Data Studio, where I'm already at this test, this script. So I'm going to bump it up just a notch, make it a little easier to read. And I have a ZDT database. Inside the ZDT database, let's add a connection. I am on localhost 52433. My username is this. My password is still in the buffer. So we're going to look at localhost 52433. Let Azure Data Studio refresh. I've got databases. Close this. I have a ZDT database right here. And let's select start from sys.tables. I've got a couple of tables in here, incident type and incident code. So nothing so far that's really that important. Let's say I want to create a new procedure. The syntax that I'm using is create or alter. This is available as of SQL Server 2016, and I love this syntax because this is a rerunnable procedure. I can take this, execute it again and again and again, and it'll work every time. What we're doing is we're going to create the stored procedure if it doesn't exist, and we'll alter it to this if it already exists. The specifics of the procedure, let's not worry too much about. We're not really focusing on the database itself, but that was the database release phase. Basically, I write this script, it goes out during database release, and then during code release, we're going to deploy our code that calls this procedure. So the blue old code doesn't know about this procedure. The green new code does know about the procedure. So we deploy our database code before that application deployment. And then I can run this and hooray, it works. Now, let's say I have an existing procedure and I want to add new columns. Quite often, I'm going to have to just defer to your code generation mechanism and basically tell you that there are two general philosophies around code generation. Number one is essentially a bag of names. So I have columns here, incident type, incident description, et cetera, et cetera. And if I want to add a new column, incident type, in my application code, I may look for the string incident type. So column incident type. The other approach is to use the ordinal value. So 0, 1, 2, 3 in these cases. Ordinal values obviously requires that your order remain consistent. So if I were to add incident type up here after incident code, I could actually break that application code. Make sure if you have ordinal based lookup of columns that you always add to the end. That way you add new columns after your existing columns. If you have key-based lookups, which is definitely the better approach, you can add them wherever. So just understand how that application code interfaces with your database procedure, and you'll be okay. When you want to add a new column, all we have to do is run this during the release phase, and everything will be fine. The old code, that blue code, doesn't know about the new column, so it doesn't even look for it. Even if your code lookup, your mapping is ordinal based, we added this at the end, so it's not going to break that code. Green, new code, is going to know about this new column, and we already have the column. So we're in good shape here. Okay, so we've added columns, but what happens if we want to remove a column? Suppose that our developers say, well, I can figure out incident type. We already know this stuff, and I can, in this case, remove incident description because maybe our application doesn't actually use incident description, and we want to try to minimize the number of unused columns. So here's the new process. Create or alter a procedure. Here's a little note, 0, 1. So our prior was get incident codes, and now I have get incident code 0, 1. I have to create a new procedure. The reason for this is after my code deploys here, my blue code expects this incident description value. My green code doesn't look for it anymore. But because the blue is supported after my database deployment, I still have to support old code and new code. I can't simply remove that column from my stored procedure because any old code that calls it will break. So instead, I'm creating a new stored procedure. So what happens is new code is going to reference this new procedure. Old code references the old procedure. Both procedures run side by side for some amount of time. So I create this new procedure during the deployment phase. And go. So create this new procedure during the deployment phase. And then in the code release phase, we're going to understand that I now have blue and green. Eventually, we'll have just green, and green only looks at procedure 01. Doesn't look at the old one. So in our database post-release, I can get rid of the old procedure. So now we're at a point where the only procedure that exists is 01. All right, so next up, you can see we've got a lot of demos. Next up, what if I want to add an input parameter? Maybe our calling code says, well, I can look for everything that is based on an incident type ID. This is going to involve a new procedure because we are changing the interface. The old interface was you call this thing with 0 parameters, and I give you back a result set shaped like this. Our new interface is you pass in a parameter for incident type, and I give you back these results. Now, if your code generator or your way of converting or interfacing the stored procedure with application code, if this can automatically interpret nullable parameters and understand how to work with them, then you don't necessarily have to create a new procedure. You could simply alter get incident codes 0, 1. But in a lot of cases, code generators I've worked with don't work that way. They require, if you have an incident type ID there, they require a method signature that includes incident type ID. They're not going to have a nullable default. So this is the most likely scenario. You might get lucky and have a code generator that works more effectively, in which case you don't have to make this as a new procedure. You can just alter the one you have. Nonetheless, we're going to create a new one, and we're going to say in the where clause, have our filter. So let's connect. There we go. Now we're connected. We're going to create this new procedure and deploy it out. In our application code, just like before, we switch to the new version of the app that passes in incident type ID. And database post-release, we get to drop the old procedure. All right. So next, what if we have a table type, user-defined table type? Well, here I have a new connection. There we go. So I don't have any table types right now. I'm going to create a new table type called incident type ID. And by the way, this is prep phase. This is basically a prior deployment. I also created this new procedure that gets incident code by type list. So basically our developer said, I want to be able to pass in a collection of type IDs and get everything related to those types instead of just one. So we created a new procedure to support multi-select. Now I want to make a change. I want to add incident type as text because they found out that, you've been adding incident type for us, but we already know what the incident type is. So let's remove this join. We'll make the query a lot faster. The way that we're going to do this is to create a new type. So I have Raleigh 2014 incident type 01, and I'm going to create a new procedure based off of this type. The reason is that I cannot alter an existing table type. So I can't directly alter incident type. What I can do is create a new one and then create a new procedure that references that new one. So one thing that I do want to point out is that this is going to be new procedure. This is going to be a new table type. There's a lot of new stuff coming into here. And I guess I could conceivably directly alter the procedure, get incident type code by type list, the original one. But if I altered the old procedure to use type 01, that's going to break existing code because it's expecting the old table type that has a particular shape. So I don't want to do that. So I'm going to create a new procedure. Then, in the code release phase, we switch over. Blue is going to look at the original get incident code by type list. Green is going to look at get incident code by type list 01. And then when we're in post release, we can drop the old procedure and then the old table type. Now, incidentally, I have in my links at the end an article, a blog post by Michael J. Swart, who shows how to do this more effectively. This is something that I learned about after creating this talk, and I'm still showing this technique because I want to get this concept in your mind. But Michael does show us a cool way of effectively swapping out the two by renaming them. So check out those links, and I'll include it as well in the description for this video. Okay, so I don't want to save my changes here. Next up, I want to refactor a procedure. Let's suppose that I try to double click on this. Okay. I have a procedure that currently looks one way, and I'm going to make some changes. Maybe I'm tuning the procedure. Maybe I'm adding some hints. Maybe I'm joining to different tables. I'm breaking out joins to views to hitting their constituent tables. Maybe I'm removing function calls or adding function calls if need be. But what I'm not doing is changing the signature. You still get the same inputs. You still get the same shape of a result set. As long as those two things are true, I am refactoring the procedure. And if you refactor the procedure, the only thing you have to worry about is the database release phase. So I can do whatever I want inside here as long as my application understands that it has this interface. So app code doesn't need to change at this point. All right, that was stored procedures. And I know there was a lot there. So I do have some recap slides that show you the process in each phase along the way. So if you want to study those a little bit more, you're welcome to. I'm not going to walk through each one of them here because there are a lot. I do this for every one of the demos that I show. So that way you have an idea of what we're doing at each step of the process. Next up, let's talk about tables. I'm going to hit a lot of scenarios here. So let's start with some demos. All right. Connect once again. I'm going to have to keep connecting. I'm going to have to keep fighting with my desire to click immediately and also fighting with its desire not to remember my password. All right. I'm going to create a large table. This large table has 4 million rows. Why 4 million rows? Well, let's, I'm going to run the whole thing at once while I talk about this. And it is currently running. So 4 million rows is going to give us just enough disk utilization that I can't trick you. The idea here is it's going to take a few seconds to run a query, and I'm going to have blocking if it'll be obvious if I'm blocking. If I have a 20 or 30 row table, the changes are so fast that it's really hard to see if there's blocking. In this case, changes will be at least several seconds, so I'm not going to be able to trick you. That's the idea behind it. Looks like it's still executing, So that's good news for us. Okay, finished. Now, I have the heap and I have the table, and I'm going to create a stored procedure that will retrieve random records. So what's going on with this procedure? Well, basically, the procedure is intended to scan the table. Again, this is part of not allowing myself to trick you. Basically, I have to scan the entire table to get back a random subselection of rows. What that means is that if I block even one row in the table, we're going to see it because I have to scan the whole thing. So if I have a lock that I'm holding that's just on a few records, we'll still catch that. Okay, let us connect. Look at that, patience pays off. The first thing that I want to do is add a nullable column. So what I've got here is I've got my large table and I want to add a new column that is allowed to be null. And in any recent version of SQL Server, this is a metadata only operation. What I mean by that is we're not changing any of the tables. What we're doing is we're changing a record in one of the system tables to indicate that there is a new column, but that all of its values are null. In order to do this, we take a schema modification lock on one of the system tables. We take a schema modification lock on our large table as well. So the schema modification lock on dbo.largeTable is going to prevent anybody else from reading that table or writing to that table or changing that table while we're doing our work or while we intend to do our work. This is good for us because it means that when I'm done running this query, I'll know that I have this new column and that something weird hasn't happened to corrupt my data in between. Where it's bad for us is I may block other users because when I want to take a schema modification lock, that means people aren't going to be allowed to read from the table. They're not going to be allowed to write to the table. They're not going to be allowed to modify the structure of the table. Well, your app probably isn't modifying structure, so that's not too big of a concern. But reading and writing are those are two of the most important things we do with tables. So during this time, anybody who's trying to query that table, not going to be able to do much. But running this operation is milliseconds. So this is back to my point that if we can perform an operation in less than the amount of time that it takes to blame the network, we're good. If somebody is blocked for 2 milliseconds, they're not going to notice that in almost any application. If you're at a point where your application notices 2 milliseconds, we're on a completely different plane of deployment. At that point, we're not making deployments. We're having to take the system down or do something radical to deal with the fact that your variance is so narrow. But for anything, especially a web application, if it's less than about 2 seconds, I'm personally not that concerned. And it would be hard pressed for a user to tell me that, yep, there was a deployment right at this time if they had a blip of 2 seconds. All right, let's connect to this. Now, I want to add a non-nullable column, but I'll have a default constraint. So alter table, large table, add a new column, non-nullable column with default. So not null, but I have a constraint. And as of, if I remember right, this was SQL Server 2012, Enterprise Edition. That is a metadata only operation. This was brought into other editions later on, like Standard Edition. But again, I don't have to add specific text in old versions of SQL Server. You go back to SQL Server 2008, it would have to add the column and add that text for every row in the table. What that meant was is locking your table for the entire time that it adds the new column. So that's not zero downtime or near zero downtime. That's possibly quite a bit of downtime. This is one advantage to moving up to newer versions of SQL Server, because more of these operations become metadata operations. They become just a couple of system table changes and you're good types of operations. So let's say I have a nullable column that I would like to backfill because I am going to add this column, but I don't have a good default. So we're going to add some non-default column. Let's do that. For each record, I would like to update this new column. And to do this, I'm going to create an index, a supporting index that exists just for the duration of this update. This index, I'll create it online. What an online index means is, while the index is being created, people can still read and write. So they can read from the table, they can write to the table, and everything goes on just as normal. Once this is ready, basically the index is full, it is taking care of all of the writes, including the writes that happen while the index is being created. It's going to take a schema modification lock and essentially swap in that index and say, hey, here's a brand new index that you get to work with. So I'm going to run this, and just to show you, let's run get random records. We can see here that, yep, I'm still getting data back. My index is still being built. So I'm able to successfully query this table while the index is being built. The one spot where I won't be able to query the table is right after it's built and when it gets swapped in. So for that couple milliseconds, I'm blocked. This will take a moment to finish up. It looks like it might have just finished. Yep, took 34 seconds to do. So now, updating records. I could update all the records at once, but that can be a fair burden on my transaction log. So instead, I'm going to update 10,000 rows at a time. I'm going to find the records where some non-default column is null. And if I come up here, my non-clustered index is on some non-default column. So what is nice about this pattern is that as I have fewer and fewer null values, this query actually gets faster and faster. So while I'm running, let me explain what I'm talking about. If you think about a pattern to update a table, let's say you have a big table and you say, I'm going to update the rows where some value is not set. You start at the beginning and you move on until you get to 10,000 rows. You say, cool, we've updated these. Well, scanning this much of the table, not too bad. But then for the next run, we have to go a bit further. So it gets a little slower. Then we have to go a little further. Then we have to go a little further. And by the end, we're doing basically full table scans every time. By contrast, if we have this nice supporting index, we start over here where the value is null, and we grab the first rows. Cool, we're done. Well, as we update those rows, they're no longer null, so the index gets reshuffled around a little bit. We find the next set where null is, and then we go. And we find the next set where null is, and we go. And each time, we're only getting a very small number of records. We're only reading a fairly small number of pages because we have that appropriate index. And as you get fewer and fewer rows left that are set to null, our runtime is essentially linear for each operation of 10,000. Versus something that grows considerably because we're scanning more and more of the table. Okay, this is still going on. And by the way, while I'm doing that, of course, I am using read committed snapshot isolation, so I can still run my queries while this backfill is happening. So this can happen during pre-release. All of this, as I mentioned in the note, is database pre-release phase. It doesn't affect our end users. Now, once we're done, we have any deployment scripts that call the new column. So I may add new stored procedures, or I may alter existing stored procedures to include the new column. Application code may reference that new column. And once I'm totally finished, it looks like it is totally finished. It took about 2 minutes to do. I can drop that index. So that index is no longer necessary. It was only intended to support that backfill operation. Now it's no longer useful. We can get rid of it. Okay, suppose I want to remove a column. We have no constraints on the column. This is about as easy as columns get. Alter table, drop column. Done. Here's the assumption. I didn't have any stored procedures or any code that referenced that column. Of course, if I have stored procedures that reference the column, I'm going to follow the advice on stored procedures to remove columns, which means I have to version it and reference the new version and application code. This is in database post-release because I am getting rid of something. Let's say I have a column that has a database constraint on it, a default constraint in this case. Well, in the database post-release phase, this is a typo, I am going to drop the constraint and then drop the column. So we've got to connect once again to this database, run it, and these were metadata operations. We had data in here, and behind the scenes, there's a cleanup process that'll actually that'll make sure that, okay, if I rebuild indexes, I'll be able to get back that space. So there's nothing that's automatic. If I delete lots of data, let's say I have large columns that were packed with text data or varchar data that was fairly significant size, I don't get back that free space immediately. I'll need to rebuild indexes in order to gain back that space, because this, all it did was essentially say, yeah, don't worry about that column anymore. Those references are no longer valid. But it doesn't delete anything. It doesn't free up any data. Suppose I want to make a string column longer. So here I have varchar. It was varchar 50. I want to make it varchar 56. This is a metadata operation. The reason it can be a metadata operation is if your column, if your data was already going to fit within 50 characters, it's going to fit within 56 for sure. There's no possibility that you'll have strings already in that table that will fail. By contrast, if I'm shrinking varchar, we are going to see what that looks like. Notice that it was not a couple milliseconds. I'm going to cancel this operation. This locks the table. This is going to force you to scan the entire table because we don't know if there are strings that are more than 50 characters long. If there are, this operation has to fail. We can't leave in a state where we have invalid data. So I've already rolled back my transaction. So instead, what I'm going to do is add a new column, backfill, drop the old column, and rename the column. So it's a multi-phase process. In the pre-release phase, we're going to add some other column 2. So some other column, and 2 will be our new 50 characters long string. For each record, I'm going to update some other column 2 and make that whatever it should be. So I want to do this in batches with a supporting index. I'm going to create that index online, and here it is where on some other column, where some other column 2 is null. So this is a different pattern for an index. Here, sort of like that first index, I am making sure that I'm going to get the same size page every time. I'm not going to have progressively longer and longer scans. So I'm going to have the same size scan because as we update records, the number of records in this index will decrease. So let's create this. And we're just updating the first 10,000 rows in the index. Of course, while this is going, because it's an online index build, we can query large table. We can execute any procedure, including get random records. Then, once this query finishes executing, probably going to be about half a minute or so, we're going to create a trigger that inserts into both columns. Triggers are normally a bad thing. At least, yeah, it's in the minds of a lot of data professionals. And I'm generally in favor of that statement. Triggers have their major downsides. However, in this case, we have a pretty big upside. That pretty big upside is the application code does not know about this column. My trigger can ensure that any time we modify a record in large table, that we ensure that some other column 2 is the same as some other column. So I'll create this trigger. And that means if I insert new rows into the table, notice that I only inserted into some column, some other column, but the trigger made sure that some other column 2 had a correct value. And by the way, the trigger just sets some other column 2 equal to some other column. So if you do have strings that are more than 50 characters long, this will give you an error. Keep that in mind. I don't get into it too much in this demo, but you might actually do something like, if you want to silently truncate, left 50. If you don't want to silently truncate, maybe you do want to throw an error and have your application code updated to say, oh, this is no longer allowing 56. It's only going to allow 50. So just keep that in mind. If I update, of course, it updates. It manages both columns, whereas all the rest of these are still null. So now we can run this backfill process. This backfill process is updating 10,000 rows at a time where some other column 2 is null. We know that if some other column 2 has a value, we don't have to update it because the trigger is handling that for us. We only need to hit the values where some other column 2 doesn't have anything, where it is null. And while that's going, people can still insert into the table. Here, let me do this in a different window. See, we still insert into the table just fine. So we can still work with the data just fine. Everything's still valid while we're performing our backfill. This is near zero downtime. It's happening during the pre-release phase, and our application doesn't notice it. Then, in the database release phase, we don't really have to do anything because we're going to rename the old column and then name some other column 2 to some other column. So that way, we basically swap out the columns And our app doesn't need to change either. What we do need to do is wait until this query finishes, probably going to take about 2 minutes. So let me talk through what we're doing in the post-release phase. Here, we're going to begin a transaction. This has to happen in one transaction to prevent people from seeing the code in a weird state, to prevent application errors. So I'm going to begin the transaction. I'll get rid of the index, that supporting index, because it references the table column names, some other column two. We're going to drop the trigger. So I need to make sure that nobody's inserting into our table because we're getting rid of that trigger. So we may lose data if we have a gap. We'll drop some other column, and then we'll rename some other column 2 to the original name. What the net result of this will be is a table where we have some other column, except that instead of a varchar 56, it'll be a varchar 50. So as this finishes up, I'll be able to run this, and this is a blocking action. I am purposefully putting into an explicit transaction. I am going to take a schema modification lock right here and another one right here. So basically I'm holding the schema modification lock. And then I'll commit the transaction, give up my locks, and allow people to query the table still. The advantage to doing this is that because you're blocked, you won't actually notice the switcheroo. It'll happen, and then the application procedure calls, when they're unblocked, will just read from the new column without noticing. So let me pause this until it finishes executing, and then we'll jump right back in. All right, this took just over 5 minutes to do, but again, we didn't stop anybody from doing anything, so we're good. This operation took 171 milliseconds, tenth of a second. Again, nobody's going to notice. So, what if we want to rename a table? Well, and we're going to take large table and call it test large table. To do this, here's what I would recommend. In the first step, the database release phase, we're going to open up an explicit transaction, rename the table, and then create a view as essentially select star from the table. The reason I want to do this is because at this point in time, if anybody is still querying large table, we don't break their code. So application code hasn't updated yet. We need a way of protecting that application code until everything's deployed. So application release process, we alter any procedures that call large table to call test large table. We update any application code that references large table. The database post-release, drop the view. And that's how we rename a table. And I'm going to rename it because I'm actually going to need that name again later. So let me kick this process off. Actually, no, I'm not going to kick this process off. I'm going to go back here. Say table recap time. So this was the process for everything from adding a nullable column to backfilling a column. Notice that the steps get pretty long. There's a lot of work involved here. This is a lot more complicated than simply saying, we're going to take a 1 hour downtime and just make the changes offline. If you do that, this list drops to about 1/3 of its length. So it's a lot easier to do when you have downtime. But if you're near zero downtime, well, there's a way. It's just going to be 2 to 3 times the development effort. So let's look next at index changes. We're going to look at 5 scenarios here, starting with the simplest one, adding a non-clustered index. So let's hop on over to our demos. where I tried to run it just a little bit too early. Create a new index on large table on some column. I'm going to say online equals on. This is Enterprise Edition only. Even SQL Server 2019, if you want online index building, you have to pay for Enterprise Edition. But that's going to allow me to do this and let everybody else just continue working on what they have. You can insert rows into large table. You can update large table. You can delete rows. Everything will work until this index is ready to swap over, in which case we'll have that schema modification lock. We'll swap in the index and we're good. Dropping index, of course. Drop index if exists. Next large table on large table. This you can do in standard edition. This is a metadata operation in standard edition. Just have to make sure this is done, and it is. So let's run that. And we've dropped the index. So this one is near zero downtime if you have Enterprise Edition. By the way, making it online equals on is going to make this operation slower. It will take longer. This is the trade-off. It will take longer to do. It may require more disk space to create the index, but you'll be able to continue working while it's going on. If you set online equals off, it'll be faster, but that table's locked while the index is being updated. Drop operation, effectively it's metadata, so it's going to be fast. Working with a clustered index. This is where online versus offline really makes a difference. Because if you are using online equals on, you may need approximately twice as much disk space for the index. I have to say approximately because if you go from a heap to a clustered index, depending on whether you're compressing it, like here I'm using data compression equals page, may end up needing less than 2x the space. If I have a very fragmented heap, it may take less than that amount of space. If I have a very compact heap and I'm creating the new clustered index, it may actually be more than twice the size of the heap. So don't get too hung up on exactly 2x. Just think I have my existing heap and I have my clustered index that is being built in the background. And I'm going to, if I have a 100 gig heap table, I'm going to need approximately 100 gigs of free space to build that clustered index. And then when it's done, essentially we have a switcheroo operation where the database engine says, okay, stop looking at the heap version, start looking at the clustered index version, and boom, now the table is going to look at the clustered index. And this heap, go away. So we're just going to have the clustered index associated with our table at that point. The database release phase, we don't necessarily need to do anything, but here's where we could perhaps change procedures to support the new clustered index. So maybe focus on queries, changing them to say where some column equals X, or basically taking advantage of the fact that we now have a clustered index. All right, next up, while this is running, let me just hop to the next operation. What if I want a clustered index that is not a primary key? This old one, well, this wasn't a primary key either. So I'm going to change the clustered index when it's not a primary key. First off, let's make sure that we have the clustered index, which it looks like we don't. CIX large heap. Okay, so this took 1:59. It's done. CIX large heap on large heap. So we're looking CIX large heap and st.name equals some other column. You say, oh, okay, it's on some column. So we haven't done it yet. We're going to create a clustered index with drop existing equals on. So if I keep the same name, I can change the contents of the index, use drop existing on, and it will simply run through, do its process, and when it's totally finished, return and say, okay, I'm done, and I'll now have some other column as my clustered index column. This is what you can do if the clustered index is not the primary key. If it is the primary key, a little bit different. So I'm going to look at large table. So I guess I will have to wait for this to finish. Okay, sorry, this is on large heap, so I can actually just let it go. I'm going to begin a transaction and drop PK large table and add a new non-clustered primary key constraint. So I have a little note that it should be fast. Here's where I'm kind of pushing it for people. I'm going to run this thing, and right now, that table's locked. If I try to query it, I'll get an error. Or, excuse me, I won't get an error, I'll get blocking. But it took 5 seconds. So basically, if someone tried to query it during this time, they'd have to wait up to 5 seconds, which is probably at the very, very edge of, it might be your network. Maybe reboot your router. Everything will be fine. It's on the very edge. But for this demo, we're just going to live with it. Then I can create a clustered index on large table on some column. And this is an online operation. So while that's going on, of course, I can execute my stored procedure to get random data. Come back to this. It looks like this one finished. This is probably going to take a minute or two. So while that's running, let's continue on. This will be for the next step in the process. And I'm going to create a parent table. I'm going to recreate large table. So let's just cancel this operation, because you get an idea that at this point, we've created clustered indexes, we've separated out the primary key from the clustered index, and so we can see what things are online, what things will cause blocking. Spoiler for later, working with primary keys causes a lot of blocking. All right, while that's going, come back to the slides, talk a little bit about our recap, and we can see that in the recap, there's not a huge amount of work to do when you're working near zero downtime and talking about indexes. But for constraints, the story is a little different. So we're going to look at 4 different scenarios, and let's come back to the demo already in progress. Looks like this is still executing, so we may have to give it a moment to wrap up. But while that's going on, let's talk about adding a default constraint. We've already seen this in the example of creating a new column with a default constraint. But in the more general case, adding default constraints, metadata operation. So this is on some column, which is definitely not null. It is definitely not empty. Some column, not null. So I can run this, 35 milliseconds, and it's done. What if I want to change the default constraint? Well, there is no alter constraint that I can use for default constraints. Instead, I have to drop and create. So I'm going to drop my old constraint. I'm going to create my new constraint. But these are, again, metadata operations, a couple of dozen milliseconds, not the biggest deal. What if I'm working with a unique key constraint? Creating a unique key constraint requires a schema stability lock. So let me start running this, and while that's going, okay, so I've rolled it back. What I'm going to do is this. I'm going to leave my transaction open. Oh, I was hoping to. Notice that I'm currently blocked. Currently really blocked. It's like I can't really see anything that's going on right now because I have those locks. As soon as I release this, I roll back the transaction. And it'll take a moment to roll back the transaction. But as soon as I get that finished, these two will free up. Okay, so I had to kill the session because Azure Data Studio was being a little funky with me. But after I killed it, now I got the ability to see my procedures and I could say execute. Let's go back to script number 43. Working with that unique key constraint. So creating a unique key constraint does cause locking for the duration of the constraint. Instead, what I would recommend is using a unique non-clustered index. That way, I can use with online equals on. Unique constraints don't allow you to create them online. So I will instead create a unique index, and I can later on modify that unique index by dropping it if it exists, if I want to add a new name for it, or simply saying drop existing equals on. So I can run this operation, and while I'm doing that, come here and still run get random records, and it'll get me random records because that table still is available while I am creating the index. It's going to apparently take a moment, but we can see, it does actually return the results, and I'm still creating that index. So online equals on does the trick yet again. The next scenario I want to look at is other constraints. Most constraints outside of default will cause blocking because it's just in the nature. Their job is to protect data. And in order to protect the data, they have to be able to stop operations while you're modifying those constraints. So dropping a primary key will block. Adding a check constraint will block because it has to scan through the whole table to make sure that existing rows are valid. Adding a foreign key constraint will block your table as well as the parent table. So let me give you an example of that. While we're waiting for this to finish, I'll close that window, make sure that this is done, and it is. We're going to add a foreign key from large table to parent table. And it was really fast. Unfortunately, that was a little too fast. But if you absolutely need to add a foreign key constraint on a table that exists and has a lot of data, and you can't take more than a couple milliseconds down, you can build a new table that has these constraints. So let's say you had that historical table that was really awful and you want to try to fix the data problems using the tools available to you. Well, unless you can take a downtime, we can create a new table that has all of those constraints. We can create a trigger. That trigger will insert into the new table anytime there's an operation on the old table. So I managed to handle insert operations, update operations, delete operations. Got to be able to handle all three of those. And then we have a running process that will operate on the table. So it'll operate on the lowest incremental value here, the minimum ID on large table, and will basically go 10,000 at a time moving forward from this ID. It's a bit of a hacky solution. If you if you really think about it, but it is a very effective solution because the minimum ID basically is saying, I'm only going to have to make one pass through on this. If this is the type of table that we are actually going to use an identity integer on, I just need to make that one pass through. If we don't have an identity integer, I don't necessarily want to use this pattern. I may use a different pattern that will be a little bit more complicated. So I'm going to move on from that and run this script. Back to the slides. Recapping each of these constraints. Basically, default constraints are easy. Unique key constraints use a unique non-clustered index instead. Other constraints, if you can, take a downtime. If you can't, it's a lot more complicated. Let's talk identity columns. There's a couple of cool things you can do with identity columns. We're going to add an identity column to an existing table. We're going to reseed an identity column, and we're going to change the data type. Let's hop over to our demo here. Looks like it is still running, but I'm okay with that. I'm going to close this. We'll let it continue running as I connect back to my database. We're going to add an identity column to a table that's missing one. So let's look at large tables definition now that we're done loading. We have large table that has an ID column. It's an integer, but it's not an identity column. Instead, we've preceded with some value. It looks like we have 10 million rows in here. So a lot of rows in here. What I want to do is make it a table with an identity column. So what I'll do is create a switch table, large table switch. Then we're going to use a neat feature in SQL Server, even available in Standard Edition, if I remember correctly, to switch partitions. So here's what's interesting. Even though I've not defined partitions in SQL Server, I've not defined that this table is a partitioned table. Well, there always is a partition. And as long as the structure of the two tables, the table that you're switching between, as long as those structures are exactly the same for what matters, we can swap and basically swap all the data over to one. So in this case, I tried to be explicit about all the things that matter. It turns out identity-ness is not something that partition switching cares about. It doesn't matter if one column is defined as an identity integer and the other is an integer, not an identity integer. So what I can do is switch large table to large table switch. And I'm actually going to do this one step at a time just so you can get an idea. So I've already created this table, and I can say select top 10 from large table switch. There's nothing in here. If I select star from large table, I've got data. So we switch. This is a metadata operation. All of my data has moved over to large table switch. Large table doesn't have anything anymore. Then I can drop large table. I can rename my switch table. I can change the name of the primary key constraint so that I don't even have the word switch in there anymore. And I've got a rough idea of how many rows there are in the table, so I'm going to set the reseed value higher than the max value in the table. If I don't do this last step, the first time someone tries to insert a value into large table, they're going to try to insert the number 1. We already have the number 1. So I need to reseed it higher than what our maximum ID is, which is 10 million. So in this case, I've set it to 25 million, just in case between the time I analyzed that table and when I did this operation, maybe a bunch of new rows were added. And large table switch is gone. So if I try to query large table switch, there's an error. That table's not there anymore. It's been renamed. And ID is now an identity integer. So we added an identity column to an existing table by taking advantage of partition switching. This was all essentially metadata operations. Users don't even know that they've had the rug pulled out from under them. Next, reseeding an identity column. We've already seen the operation is metadata. So I can run this whenever I want. It won't affect users. If I want to change the column type, let's say from integer to big int, I can't simply, it's not an incredibly easy change. I can't alter the data type on the identity integer. So we're going to create large table big int. We're going to create a trigger that inserts into large table big int. Insert, update, delete operations are handled. And we're going to backfill large table big int. Then when I'm done, in the post-release phase, we rename large table big int to large table. I take the old large table and I put a little delete me in there. One thing I do like to do is to put a date, delete me after January 1st, 2021, or some dates far enough in the future that we know this table will be here, but not so far that we'll never drop it. Because at some point we will want to drop this thing. If you have a drop me after date, then you'll know, oh, I'm not dropping it too early. So that's the process of working with identities. For adding an identity column to an existing table, pretty cool process. For reseeding an identity column, real easy process. For changing the data type from int to big int, or big int to int, or whatever, create a new table. Last, I want to talk about a case study, something I've gone through. As a database engineer, I was responsible at one point for working with a team that had about 200 tables, 800 stored procedures. Most of these tables had a column called client ID that was the customer. The problem is that client ID had a specific meaning at the company, and it wasn't strictly customer. It was a little bit more complex than that. The thing that it really was is a profile ID. So to bring this team in line with the rest of the company, I had to update about 150 tables, about 700 stored procedures, and I didn't have an extended downtime to do this. I had to do it strictly while things were still online. So our data architect came up with a solution. She's responsible for coming up with the idea for the proof that it worked. And then she and I worked together quite a bit to put this into practice. What we're going to do, rename client ID to profile ID on about 150 tables. That includes renaming constraints, renaming indexes. Everything that said client ID now says profile ID. Drop unused procedures, unused tables. So that was one of the things that I did, try to figure out what things are not in use. Rename client ID to profile ID on about 550 procedures. And while we're at it, let's refactor those as well, because many of these procedures haven't been touched in years. A lot of them are using older practices. They weren't in line with what we wanted as a database team. Any SSIS packages needed to use profile ID. Any ad hoc queries needed to use profile ID. So everything had to switch over. But again, we couldn't take the system down. So here's the process. We start off in this world where orange means client ID. Everything's client ID focused. So our first step, pre-release. Reformat, refactor procedures. Look for unused procedures. So areas where we looked, if it's in the plan or procedure cache, it's obviously in use. If it's in the code base, it's probably in use. If it's in a SQL agent job that's running, it's in use. The SSIS package, or if it's in some metadata table, if it's in anywhere where you can find it in source control, anywhere where you can find it as referenced in another procedure that's used, well, this thing's in use. Now, if an object is broken, like if I try to query a view and it returns an error, that is obviously not in use, because otherwise it would have fixed it. So we're able to drop some of those broken views, broken functions, broken procedures. Those were obvious candidates that, okay, well, this stuff's not working. It's not actually being used. And during this phase as well, there were a couple of people whose main focus was create lots and lots of database tests. See how things worked prior to our changes. And that way we can run the tests again after the changes to make sure things still work. So moving forward in the pre-release phase, we added a new column to each table that had client ID. We had profile ID as a nullable integer. Then we released some temporary procedures that took both client ID and profile ID as parameters. We scooped out the logic from current procedures and put it into the temp procedures, and did is-null checks on profile ID and client ID, and turned those app level procedures, so the ones that were actually called by the application, into shells that called the temp procedures. So it kind of looked like this. We have on the right-hand side our application code right up here. Next to that is the code-facing stored procedures. I'm really bad at spatial awareness, apparently. So code-facing stored procedures called by the application, followed by temporary procedures that we're using profile ID. And the tables have client ID, which has a real value, and profile ID, which is null. So there's orange tinged with blue. But we're starting to see some blue on here. Blue means profile ID, of course. Release phase 2B. Change references and views and functions, and return is null profile ID and client ID instead of just client ID. By the way, this slows down queries, especially if it's an aware clause. But this slowdown was going to be over the course of dozens of minutes. So not the worst thing in the world. So we now have looking for client ID and profile ID in the stuff that doesn't face application code. But what this allows us to do is update the non-app SQL code to do profile ID and client ID checks. SQL agent jobs, triggers, stored procedures not used in the application, but maybe used by other processes, integration services projects, everything else. So again, all of that non-app code is aware of both columns at this point. We've deployed this out, and those things are going a bit slowly, but we'll deal with it. Now comes the swaparoo. Profile ID and client ID. We have a profile ID column, a client ID column, and what we're going to do is rename profile ID to profile ID 2. We're going to rename client ID to profile ID. We're going to add a new client ID, and we're going to drop profile ID 2. Here's the reason why. We could simply have, say, rename profile ID to 2, rename client ID to profile ID, rename profile ID 2 to client ID. But just in case somebody went and updated that old profile ID column while it was there, we didn't want to take the risk that there were bad values in there. So we dropped that column. We created a new empty, null-filled client ID. Then rename all the constraints, because anytime it said client ID, we could just rename that constraint to say profile ID. So what we have at this point is tables have swapped. Instead of orange client ID with empty blue profile ID, we have blue profile ID with empty orange client ID. All of the non-application code over here still is looking at both columns. So none of that needed to change right here. The application code is still looking just at client ID, but our code-facing stored procedures are aware of both columns because the temp procedures have both. So we're still good to go here. What we want to do next is start the cleanup process. Deploy the final versions of our temp code procedures. Anywhere it said client ID, we can get rid of that. We can specify profile ID. We can get rid of those is null checks. Just use profile ID. We don't need client ID anymore. And this doesn't change much on the picture here, but we do have new procedures. Instead of our temporary procedures, we have permanent procedures. Then update the non-application SQL code to just look at profile ID. So all the stuff at the bottom layer is now fully blue. Next up, we can start rolling up. So change those views, change those functions to just use profile ID. Now, here's one little tricky bit. We did have to say profile ID as client ID because there were still cases where you're querying that view and some code was looking for client ID. Just to make sure we don't break that code, we're going to return client ID, except that it's really profile ID. And at that point, all of that bottom is blue. So we can get rid of client ID, drop that column, deprecate any stored procedures that are no longer in use. And we have a lot of blue. Now the application hasn't changed. Our app developers weren't affected by this at all because we still had that interface layer of code-facing stored procedures that referenced client ID. So over time, what we started to do was have new procedures that only referenced profile ID. We stopped creating procedures that said anything with client ID. It was all profile ID. So new application code knows that profile ID is a thing. Old code is still looking at client ID. As those procedures change, as we version those procedures and support new things for the developers, they're using profile ID. So basically that code-facing stored procedures block gets smaller and smaller over time, and our application code goes more and more blue instead of orange. This was, by the way, something that application code took literally years to finalize. And frankly, there's probably still parts in the app code that are still saying client ID. But that database code, we released it. It was all out over the course of a few hours. We had to roll back 2 procedures, one of which we dropped because it turned out it was an ad hoc procedure that hadn't been run in a while and just needed to be run that weekend. And another one because we messed up. We didn't fix a reference, and so it did break code. So knowing that there were a couple of small things, but that we were able to get 150 plus tables, 700 plus procedures dealt with, not a bad day. So wrapping up here, zero downtime, scare quotes. This isn't for every company. Frankly, my strong recommendation is if you have the ability to take a downtime window, take it. Your deployments will get a lot easier. But if you don't have that window, you need these tools. It's good to know what you're capable of doing without really impacting your customers. If you'd like to learn more, grab the slides, grab the demos, links to additional resources, go to csmore.info/on/ZDT. If you have any questions at all, please feel free to reach out, drop a comment in this video, hit me up via email or Twitter, and let me know what you think.